Hey everybody, welcome. These are the notes for Chapter 8, Day 2. And in this video, we're going to take a look at solving differential equations by separation of variables. So we look at the first example. It says, solve for the general solution dy dx, which is equal to x squared plus 2 over 3y squared. Now, the term separation of variables essentially is telling us to get the y's on the same side as dy and the x's on the same side as dx. So in order to do that, in this case, we can get there by cross multiplying. So we can cross multiply to get the y's on the left and the x's on the right. All right, so if we do that, we would get 3y squared dy. So 3y squared dy equal to x squared plus 2 dx. All right, so once we've done that, we cross multiply to get the y's on the left, the x's on the right. And you'll notice that the y's are with the dy's and the x's are with the dx. The second step to this process is going to be to integrate both sides. So we're going to integrate both sides. So when we do that, you'll notice that we're taking the integral on the left with respect to y. So the integral of 3y squared is simply going to be y cubed. And then you could think of that as plus c equals. And when we integrate the right, we're integrating with respect to x, which is the variable that we have. And we get 1/3 x cubed plus 2x, and then plus c. Now, one thing you might want to pay attention to is that there are two c's, and they are different. They could be different values. But because they're both constants, we don't want c's, and we don't need c's to be on both sides. So if you were to move, C1 over with C sub 2, it's just going to become some other constant, some other C. So you really only have to put the constant on the right side when you're solving these. But I just wanted to show you getting it on both sides so I can explain what was going on. So really, we just want to have 1/3 x cubed plus 2x plus c. And just purely leave the c on the right side. And you don't need to worry about it on the left side moving forward. All right, and then the last thing is going to be to isolate y. So in this case, y cubed is equal to 1/3 x cubed plus 2x plus c. Now y is not technically isolated in that situation. In order for us to truly isolate y, we would need to take the cube root of both sides. So the cube root of 1/3 x cubed plus 2x plus c. Now, there are possibly times when you'll see it left as y cubed equals, but really when we're looking for that general solution, we want y to be by itself. So we want to cube root both sides. All right, and that's how we are going to solve these differential equations using separation of variables. All right, here's number 2. So in this case, notation's a little different. It says solve for the general solution x y prime equals y. Now, one thing I think that's going to be helpful is if you rewrite y prime. And what this is going to look like is x dy dx, which is another way of writing y prime, is equal to y. So if you write it like that, now you have it in a form where you can get the y's on the left and the x's on the right. So what I would recommend is that you guys pause the video at this point and try that on your own. All right, so if we were to move forward with this and we want to get the y's on the left, we're going to have to divide by y. All right, and we're going to end up moving the x and the dx. So when we divide by y, you'll end up with 1/y dy equals. And then think about moving the x and the dx over. That's going to be kind of 2 steps, or you can think about multiplying by the reciprocal. But really, you're going to divide by x, giving us 1/x, and then multiply by dx, giving us dx. So we end up with 1 over y dy equal to 1 over x dx. At that point, we can integrate both sides. So the integral of 1 over y is going to be the natural log of the absolute value of y. And then the integral of 1 over x is going to be the natural log of the absolute value of x plus c. So there's where we want the c. All right. Now, what we want to do at this point is we need to get y alone, which means we have to cancel out ln. So you want to try to think about what is the inverse of natural log? Well, it's base e. So we're going to take base e on both sides. All right. When we do that on the left side, we end up with y equals. On the right side, we get e ln of absolute value of x plus c. Now, the domain of e is going to be greater than or equal to 0. So we don't necessarily need the absolute value in this situation. But one thing that you are going to end up seeing is that this can be simplified and rewritten. And it uses properties of exponents. So you can think about this as e to the ln of x and then times e to the c. All right, and that comes from when you multiply exponentials, you add the exponents. So we're going the other way where you have a base to a sum. All right, the exponent's a sum, so we're basically splitting it up. And then the reason why that's important is because e to the c is just a constant. All right, and because we haven't identified what that constant is, that just becomes c. So you could think about this as y equals ce to the ln of x. But then hopefully some of you guys are recognizing e and ln are inverses of each other, so they're going to cancel each other out, which means this really simply becomes y equals cx. And that is the answer there. So a little bit going on there in terms of going back to properties of exponents and remembering those things. But hopefully as we go through these, those things will come back to you. All right, let's go ahead and take a look at the next page and see what we got going on here. All right, so in this time it says, find the particular solution of the differential equation shown if it has an initial condition y of 1 equals 2. So now when it's talking about the particular solution as opposed to the general solution, we need to know what this initial condition is so that we can use it to find c. The start of the problem is going to be identical. So again, just like the other problems, I would recommend that you pause the video and try this on your own. All right, now, the first thing I'm going to do is I'm going to rewrite this as 2x dy dx minus ln of x squared equals 0. And then from there, we want to go through the process of getting the x's on one side and the y's on the other side. So initially, you might do something, the simple thing is to move the ln of x squared over. So dy dx equals ln of x squared, because we're simply going to add that to the right, or add that to both sides. And then, you can kind of think about, all right, well, what are you going to do from there? Well, there's no other y. So we would have, we can think about this a couple ways. Dy dx equals. Now, ln of x squared, that 2 can be pulled out in front to get 2 ln of x. And then if we divide by 2x, that was kind of beneficial because now the 2's cancel and we're dealing with a little bit simpler expression. And then the last thing I want to do before I'm ready to integrate is get the dx on the other side. So dy is going to equal ln of x over x dx. All right. So, obviously you could have potentially done that in fewer steps, but I was trying to walk through the process of how we get there. Now that we have the y's on the left and the x's on the right, even though there is no y term, we can still integrate. So we're going to integrate both sides. The integral of dy is simply y. All right. Now, when we come over here and we want to integrate ln of x over x, it might not be obvious what's going on there, but this is going to be a case for u substitution. So we want to let u equal ln of x, because du is then 1 over x dx. And 1 over x dx is what we have right there. So using u substitution, this becomes the integral of u du. All right, that's a little bit easier to integrate. So we're going to get 1/2 u squared plus c. Plug our ln of x back in, so we get 1/2 ln of x squared plus c. All right, now we do need, that is, well, let me kind of back up. That is the general solution, okay? And based on the other two examples we did, that's what we were doing. We were done at that point. But we want to find the particular solution, and we are given this initial condition up here that y of 1 is equal to 2. All right, that's the same thing as having a coordinate 1, 2. So that is a point on our function. Well, if we come back over here and we plug those in, that's going to be 2 is equal to 1/2 ln of 1 quantity squared plus c. All right. And if you kind of think about what's happening here, the natural log of 1 is 0, 0 squared is 0, 1/2 times 0 is 0. So from there, we find out that c is equal to 2. And at that point, we can plug 2 back in for c. So we end up with y equals 1/2 ln of x quantity squared plus 2. And that is what is referred to as the particular solution. Okay, it is the solution given the initial condition y of 1 equals 2. All right, let's go ahead and move on to the next example. Guys, and I'm going to go ahead and stop the first video here, and we'll pick up on the second video. So we'll go ahead and finish the first video right there at the end of example 3.